Hello viewers, in today's class we are going to discuss one important problem from limits, right? And here we'll solve this problem, and here we are given the function f of x is equal to a raised to greatest integer of x plus x minus 1 divided by greatest integer of x plus x when x is not equal to 0, and we have to find the limit of this function when x approaches to 0, right? So here basically we have to see whether this limit exists or not, right? So what we will do, we'll find out the right hand limit and the left hand limit of this function when x approaches to 0, right? So here if we take x is equal to 0, so when we calculate the right hand limit, then we have to take a point very close to x is equal to 0, that is in the neighborhood of x is equal to 0, and this point is 0 plus h, right? And when we find out the left hand limit of this function when x approaches to 0, then we take a point very close to x is equal to 0, that is in the neighborhood of x is equal to 0, and this point is 0 minus h, right? Okay, so when we find out the left hand limit, then we are approaching from the left of x is equal to 0, and when we are finding out the right hand limit, then we are approaching from the right of x is equal to 0, right? So let us first find out the right hand limit. So the notation for the right hand limit is the limit x tends to 0, and here we have a positive sign, right? And here we'll write f of x, and we'll take x is equal to 0 plus h, right? Where h is a very small quantity, and h is positive quantity, right? So h is greater than 0, but it is less than 1, right? So we'll take x is equal to 0 plus h. So x is equal to h, 0 plus h is h, and when x tends to 0, then obviously h tends to 0, right? So now the right hand limit can be written as the limit, and we can now write this expression in terms of h, right? So we have h tends to 0 and f of x, and for x we have x is equal to h, right? So here we have f of h. So now we can write limit h tends to 0, and f of h can be written as a raised to greatest integer of h, because here we'll replace x by h. So here we have h minus 1 divided by greatest integer of h plus h, right? Okay, so now we have to find this limit when h approaches to 0, but here we cannot directly substitute h is equal to 0, right? So what we will do, we'll take help of the definition of greatest integer function, right? So see, h lies between 0 and 1, right? Because h is infinitesimally very small, right? So h lies between 0 and 1. So by definition of greatest integer function, the value of greatest integer of h is must be equal to 0, because h lies between 0 and 1, right? So here the greatest integer of h is 0. So now we can write limit h tends to 0, and we have a raised to 0 plus h. Here we have 0, and here we have minus 1, and here we have 0 plus h, right? So this is limit h tends to 0, and we have a raised to h minus 1 over h, right? So now we have arrived at a very famous limit, right? So here the value of see from limits, we know that limit x tends to 0, a raised to x minus 1 over x is equal to 1, right? So this is the famous limit, and here will directly use this limit. So the value of this limit is equal to 1, right? So the right hand limit of this function when x approaches to 0 is equal to 1, right? So now let us find out the left hand limit. Now the notation for the left hand limit is limit x tends to 0 minus, right? So this negative sign shows that now we are approaching from the left of x is equal to 0, and this positive sign shows that we are approaching from the right of x is equal to 0, right? So here we have f of x. So now when we approach from the left of x is equal to 0, we take x is equal to 0 minus h, and which is equal to minus h, and h is a positive quantity and it lies between 0 and 1, right? So when x tends to 0, obviously h tends to 0. So now we can write this limit in terms of h as limit h tends to 0, and here we have f of minus h because x is equal to minus h. So now limit h tends to 0, f of minus h can be obtained from the function itself. So here replacing x by minus h, we'll have a raised to minus h, greatest integer of minus h. Then here we have minus h because x is minus h, and here we have minus 1, and here we have greatest integer of minus h minus h, right? And again what we will do, see here we cannot directly substitute h is equal to 0. So what we will do, will try to find out the value of greatest integer of minus h, right? So for this we'll use this inequality, right? So we know that h lies between 0 and 1. So let us multiply throughout by -1. So we have 0, and the direction of the inequality get reversed once we multiply throughout by -1. So here we have minus h, here we have minus 1. So we can rewrite this inequality as minus 1, minus h, and 0, right? So we see that this negative h, it lies between -1 and 0. So from the definition of greatest integer function, the value of greatest integer of minus h must be equal to -1, because minus h, it lies between -1 and 0, right? So greatest integer of minus h is -1. So here we'll now write limit h tends to 0, and we have a raised to -1, and here we have minus h, and here we have -1, and this is -1 and minus h, right? So now as h tends to 0, here we'll get a raised to -1 minus 0. Here we'll take h is equal to 0, and here we have -1, -1 minus 0, right? So let us simplify it. So here we have a raised to -1, -1, and -1, right? And taking this -1 to the numerator, we can reshuffle these two terms. So we have 1 minus a raised to -1. So the left hand limit is equal to 1 minus 1 over a, right? Which can also be written as a minus 1 over a, right? So we see from this discussion that the right hand limit is 1, and the left hand limit is 1 minus 1 over a, right? And both these limits are not equal to each other, right? We know that for the limit of a function to exist, this right hand limit and the left hand limit must be equal, right? But here we see that the right hand limit is 1 and the left hand limit is 1 minus 1 over a, and since both the limits are not equal, so we can safely say that or we can claim that the limit of this function when x approaches to 0, it does not exist, right? So here the limit does not exist.